All right, today we're going to do Chapter 6, Quantitative Relationships. What we're going to do in this chapter is take the concept of stoichiometry that we talked about in Chapter 5, and we're going to apply it to calculate theoretical yields, percent yields, stuff like that. First of all, let me remind you, Wednesday is no class. It is lab makeup day. Now, don't get excited. This is basically a snow or a COVID day. So, no, we can't do individual labs, only the whole class. So basically there is no class because it hasn't snowed yet. Today it feels like it, but nonetheless, no class on Wednesday. Now, there is something you can do on Wednesday. The department, the state, somebody, wants to do assessments, okay? See how you're doing. Last semester there was one. This semester there are two, okay? The first one is lab safety. Now, this is a fairly stupid little quiz. Questions like, it's okay to eat in lab if it's lunchtime. Okay? No. But the lab safety quiz is here on Blackboard right underneath tutorials too. And you can earn 6 points extra credit by taking it. So, please take it. Everybody needs to get as many extra credit points as possible. Also, apparently everybody got emailed a link for a evaluation. I'm supposed to remind you to please do that. We used to hand out the paper ones, right? Those were good because I could collect them and throw away the bad ones and, whatever. Just kidding. There never were bad ones. Anyway, do the safety quiz, earn the 6 points. All right, we've seen these before. Chemical reactions. Reactants and products connected by a reaction arrow. The reaction arrow is basically an equal sign, same numbers and types of atoms on both sides, and the same mass on both sides. In order to make sure we have the same numbers and types, we put in coefficients. We said that this was stoichiometry for the reaction. And we talked about how to balance things in Chapter 5. I do it by an odd-even method. On this side, we have an odd number of bromines, even on this side. So we would double this. That gives us a total of 6 bromines, only 2 here. So we need to put a 3 in there. We also have 2 aluminums, and we need 2 there. And we have a balanced equation. Now, we said we can just look at this and enjoy the fact that it's balanced. We can also describe this in terms of moles. This basically says 2 moles of aluminum reacting with 3 moles of bromine gives 2 moles of aluminum bromide. This here is referred to as the theoretical yield for the reaction. If we take 2 moles of aluminum, 3 moles of bromine, theoretically, we should get 2 moles of aluminum bromide. What we're going to do today is to delve into this a little bit. Typically, things, reactions, when you do them in real lab, you don't do them according to the coefficients typically. In this reaction, we would put in excess bromine. Bromine is difficult to work with. We would just put in a whole bunch of bromine and only 2 moles of aluminum. We're still only going to get 2 moles of aluminum bromide. Let's see how this works. Here we have ethanol, organic alcohol, reacting with oxygen to give CO2 and water. Now, this is a balanced equation. We have 1, 2, 3, 4, 5, 6 hydrogens, 6 hydrogens, 2 carbons, 2 carbons, and we have 1, 6, 7 oxygens. So 3 plus 4, 7. It's balanced, okay? In this problem, we want to know how many moles of CO2 we're going to get. If we have 2.5 moles of ethanol. Now we're burning this in the presence of excess oxygen. It's just in the room. So, oxygen is in excess. How are we going to do this? Well, what we're going to do first is to look at our balanced equation and come up with a stoichiometric ratio for ethanol and CO2. According to our equation, for every 1 mole of ethanol, we're going to get 2 moles of CO2. So 1 to 2 is our ratio. Up here in our problem, 2.5 moles of ethanol is the given. Okay? We're going to put that in our denominator of our ratio. So, we are given 2.5 moles of ethanol. Our little ratio is 2 moles to 1, and we're trying to find moles of CO2. We start off, as always, with our given. Going to multiply it by our ratio. Moles of ethanol will cancel. That's why we put this in the denominator. 2.5 times 2 divided by 1, 5 moles of CO2. Fairly simple problem, fairly simple solution. Any questions? Well, there's another way we could do this that's a little bit faster, a little bit more efficient for your calculator. And that is to do the same problem here using two mole ratios. One is a known and the other is the unknown. Now we've already said we have a 1:2 ratio here. What we're going to do is look at our problem. We're going to identify the unknown we're trying to get and the given. So our ratio here is 2 moles of CO2 to 1 mole of ethanol. That's our known ratio. The unknown ratio, this is going to be X, our unknown, moles of CO2, and this, of course, is our given 2.5 moles of ethanol. Write this as a simple ratio, like that. A known ratio and an unknown ratio. Now, this is simpler and faster on your calculator because you simply cross multiply 2.5 times 2 divided by 1. Get 5. We can also expand this, if you like. Multiply both sides by 2.5 moles of ethanol, and we get this equation. Now, if you know, again, moles of ethanol cancel, but this is our given here, isn't it? And this is our ratio. So this is exactly the same as doing the given ratio find method, except it's a little faster. Any questions? Well, let's look at another one. Calcium with HCl gives calcium chloride and hydrogen gas. First thing you do is make sure the equation is balanced. 1 calcium, 2 hydrogens, 2 chlorines. Yep, we're balanced. All right. We're looking for how many moles of HCl. That's this guy. And we have 3.25 moles of calcium. That's this guy. So, how many moles are required? We look at our equation here. It takes 2 HCl's for every calcium dozen. Calcium is our given, so that'll be our denominator. Let's write our equation like this. 2 moles of HCl, 1 mole of calcium. Now, our unknown ratio, moles of HCl, that's X, and moles of calcium is our given. So our unknown ratio is this guy. Once again on your calculator, 3.25 times 2 divided by 1. Expanding it, once again, here's our given, here's our ratio, we cancel, do our multiplication, 6.5 moles of HCl. That's not so hard, is it? Quantitative chemistry. All right, so one year I put this on as a 2-step problem. Step 1, balance this equation. And step 2, take the balanced equation, see how many moles of molecular oxygen, that's O2, are required to produce 1.7 moles of CO2. Step 1, balance the equation. Well, gee, we have 2 carbons, we only have 1 carbon. So let's double this. Now, we have 6 hydrogens, only 2 hydrogens. Let's put a 3 out here. So how many oxygens do we need? We have 4, 5, 6, 7, right? So what's our coefficient? Well, oxygen comes as pairs, so this would be 3.5. Well, now technically, this is a balanced equation. Okay, technically it is. Convention, however, requires that they be integers. So if this happens to you, you wind up with something that's not an integer, just look and say, all right, what do I have to do here? Instead of 3.5, let's make that 7. We're going to double it. That means we have to put a 2 in here, change our 2 to a 4, and our 3 to a 6. Let's see what it looks like. Yes. So the bottom line is, if you wind up with 3.5, just double everything. All right. Hello. Come on. There it is. Okay. So here's our balanced equation now. Let's see. Let's look at this. We're looking at O2 and CO2. So our ratio here is 7 oxygens, 4 CO2s. Our given is going to be CO2. We'll put that in our denominator. So our ratio is going to be 7 to 4. That's the known ratio. Now the unknown ratio, moles of oxygen is X, moles of CO2 is the given. So, on your calculator one more time, you would do 1.7 times 7 divided by 4. Simple. We could also expand it, so we can easily cancel moles of CO2. Once again, 1.7 times 7 divided by 4. 2.975 is the calculator answer. Now, we look at this and we know we have 3 significant figures, don't we? So, how do we round this? It ends exactly in 5, doesn't it? There's a rule for that.
So if 7 goes up, so it'll be 2.9.
You round even. Any questions? Yet another one. This is chloroacetic acid reacting with oxygen to give carbon monoxide, water, and HCl. Once again, it's a balanced equation. Our two things we're looking at are oxygen and carbon monoxide. Go ahead and set up your ratio. Our ratio here is 1 oxygen, 4 moles of CO. Okay. Again, carbon monoxide is going to be the given, so we'll write the ratio with it in the denominator. Now our unknown, moles of oxygen is X. This is our given. And there's our second ratio. So, 0.26 times 1 divided by 4, something like this. That's on your calculator. And you get 0.66125 moles of oxygen. Now, we are dealing with 4 significant figures. Once again, this ends in exactly 5. So again, we round even.
Thank you.
Any questions? All right, well, there's a tutorial called molar stoichiometry. Here's what we've been doing, our known ratio, our unknown ratio, again with the given in the denominators. You are told to find the number of moles of sodium hydrogen carbonate. We are given sodium carbonate, so we're linking this guy, the reactant, and the product. First thing we would do is set up our known ratio. That's going to be 2 sodium hydrogen carbonates for every sodium carbonate. 2 to 1 is our ratio. Our unknown ratio, we're looking for sodium carbonate, that's this. We are given 0.82 moles of sodium carbonate. Once again, on your calculator, it would be 0.82 times 2 divided by 1, 1.6. Now these look difficult, they sound difficult, but actually they're pretty simple, aren't they? Let's look at one more. This is chloroethane. We are getting chlorine out as a product. 4 chloroethanes, 2 chlorines. Our ratio would be 4 to 2. This is our given, so it's going to be in our denominator. So quickly write your known ratio, write your unknown ratio from this, and let's do it. Now you can write your known ratio as 4 to 2, or you could just do 2 to 1. It doesn't matter. 2 to 1 is fewer numbers. Here's our known ratio, here's our unknown ratio. That's the find and the given. Simply 0.99 times 2 divided by 1, 1984. All right. As always, 5 points. Pretty much the tutorial on Blackboard is exactly the same as this. Okay? Now, in real life, when you're in a lab, you actually don't do many calculations in terms of moles. We don't add 0.9922 moles of something. We add grams of something, don't we? That makes sense. So let's take and apply this same concept to a mass problem. We're looking for grams of zinc oxide. We are given grams of zinc sulfide. So, zinc sulfide, zinc oxide, 2 to 2 or 1 to 1. First thing we're going to do is write our known ratio. That's 1 to 1. Again, zinc sulfide is going to be our given. I have deliberately turned this upside down just to show you you could. 1 mole of this, 1 mole of that. Now we know that 1 mole of zinc sulfide is 97 grams of zinc sulfide. And 1 mole of zinc oxide is 81 grams. So instead of writing in molar quantities, we can simply put them in as mass quantities. Now our unknown ratio, grams of zinc oxide, we'll put it in the denominator. Grams of zinc sulfide, we'll put it up top, just temporarily. That's our x. This is our given. And we would write it like that. Now at this point, you would look at this and you would say, shoot, I got this upside down, don't I? What do? Just simply flip them both over. That's all. Just like that with a click of the mouse. Just take, flip them over. Perfectly legal. And the calculation now, 25 times 81 divided by 97, 20.9 grams of zinc oxide. So converting this to mass is really simple. Instead of writing a simple molar ratio and using that, we just convert it to a known mass ratio. Let's do another one. We're taking fluorine and water, making hydrogen fluoride and oxygen. We're looking for a mass of water, that's this, and 64 grams of hydrogen fluoride. That's our given. Our known ratio here, again, this is water and HF, 2 to 4. HF is our given, we want it in the denominator. 2 moles of water, 4 moles of HF. Our ratio would look like this. 2 waters and 4 HFs. You could do 1 to 2 as well, doesn't matter. Now, in order to make this into a mass ratio, what you do is simply multiply each of these by their molar mass. Water is about 18, HF is about 20. So we would multiply 2 times 18, 4 times 20. If we do canceling, we can get rid of all the moles, and we're just left with grams. Once we do the math, this is what we get. Now, this makes sense, okay? This is logical. This ratio is logical. If you have 36 grams of water, you will get 80 grams of HF. All right, so here's our ratio. The unknown ratio, here's our unknown up here, grams of water. Grams of HF is the given. And here's our equation. 64 times 36 divided by 80, 28.1 grams. Once again, this is called a mass ratio. You make it simply by taking the stoichiometric coefficients, 2 and 4, and multiplying by the molar mass. Any questions? Well, this brings us to our second tutorial here, mass ratios. Once again, here's the definition, the molar mass multiplied by the coefficient. This is an oxide of cobalt, isn't it? So is this. What is this named properly? First of all, cobalt. It's in here somewhere.
It's the iron, so yeah, it's in the middle.
Somewhere. There it is. It's a transition metal. So we have to show the oxidation number, right? Oxygen is going to be -2, so this must be +2. This cobalt oxide, every oxygen is -2. That means each cobalt here must be +3. So, let's see, we're doing cobalt 2 and cobalt 3. There's 2, there's 3. 4 moles of cobalt 2 gives 2 moles of cobalt 3. This is also a redox reaction, isn't it? Because the oxidation number changes from 2 to 3. So, we're going to go ahead and write the mole ratio, the mass ratio, and our given is cobalt 3. For cobalt 2 to 2 cobalt 3. Now we are given the molar mass of each, so we simply multiply these by the molar mass. 4 times 74, 2 times 166. Now this is a ratio, isn't it? We could multiply this out and, do our usual thing. But it's a ratio, and we are given something here, aren't we? We could just take our given and multiply it by this ratio as it sits. 40 times 4 times 75 divided by 2 divided by 166. Everything cancels nicely. 37 grams. Any questions? All right, again, the one on Blackboard looks pretty much like this guy. All you do is write a mass ratio and multiply your given. Any questions? Well, this brings us to another topic called limiting reactants. I said that typically we would take aluminum and bromine, put in excess bromine and blah, 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 right? You could do it another way. What if we took 2 moles of aluminum, 3 moles of bromine, we would get 2 moles of aluminum bromide. But what if we only had 2 moles of bromine? The amount of product that you would get would be limited by the bromine. The smaller molar amount in a reaction is referred to as a limiting reactant. The one where you have plenty is referred to as the excess reactant. Now, limiting reactant problems are done exactly like the ones we've just done, except you have to do them twice. You do it with each molar quantity as a given. That's annoying, and that's, if you're going to be annoying, you may as well take general chemistry, okay? We're going to do limiting reactants as a concept. So let's do a concept. It's cold outside today, right? If you have children, you probably are looking in the closet for gloves for last year. And you find a pile. Well, okay. Everyone needs a right and a left, right? We have 4 lefts and 3 rights in our pile. So we gather up a couple, make a pair. Gather up another couple, make another pair. Third pair. Left-handed gloves are in excess because we got 1 left over, right? The right-handed gloves told us how many pairs we could make. That's limiting. Simple concept. You need 1 of each. Stoichiometric would be 4 and 4, right? We don't. We had 4 and 3. The right-handed are limiting. Now, on the exam, I'm not going to give you gloves, but we'll deal with something like this. Here's a real reaction. Fluorine reacting with chlorine to give chlorine trifluoride. What I would give you is something like this. We have a pot, and we have 3 chlorines, and we have 1, 2, 3, 4, 5, 6 fluorines. How many moles of chlorine trifluoride will we make, and which is limiting? So that will be a test question. All right. It takes 2 atoms of chlorine and 6 atoms of fluorine to make 2 of these guys, right? So let's take a chlorine and 3 fluorines and make a product. Chlorine trifluoride. Let's take another chlorine, 3 more fluorines, 2 more. What was limiting? The amount of fluorine. We've used it all up. What's in excess? Chlorine is left over. It's a little bit of a mind game. Again, what I would do on the exam is give you an equation like this, give you a number of this and this, and you would decide which one was limiting. It's a whole lot easier and much more fun than doing the whole problem twice. Any questions? All right. I said that from our balanced equation, we get what's known as the theoretical yield, right? We said 2 moles of bromine, 3 moles of bromine, 2 moles of aluminum, 2 moles of aluminum bromide. Again, typically, we would have excess of 1. Our theoretical yield here would be 2 moles of aluminum bromide. Here's our mole ratio. Here's our product. The theoretical yield, we say 2 moles of aluminum bromide. Now, that's the theoretical yield. Very, very seldom do you get exactly what you expect. There are 2 reasons for this. First of all, you're human. You spill things. Your lab partner sneezes and blows it all away. Something like that. And the other is a fairly practical way. Reactions proceed by following an energy pathway. Think of a mountain range as a 3D energy pathway. And most of the molecules are going to be well behaved and are going to go the lowest energy path from reactant to product. Okay? Most of them. But there's always somebody that instead of going with everybody else is going to do something stupid. Climb the mountain or whatever. Depending on exactly what the profile looks like, you could get more going this way than this way or whatever. So, theoretically, you can get a mixture of products from any reaction. That means either you're sloppy or we have multiple pathways working, but you almost never get a perfect theoretical yield. What you get is an actual yield. So overall, it's called the yield. Theoretical yield is what you predict based on the stoichiometry. And the actual yield is what is left in the pot when you're done.
So it's a product.
Percentage of the two gives us the percentage yield. Percentage yield is something that's very important in chemistry. You do a reaction, you know what you put in, you see what you get out. You want to get the best percent yield you can, and what you do really in lab is you will fiddle with conditions to get that up. Percent yield. So, whenever you think of percent yield, think of popcorn. So we've done gloves and popcorn now. Here we have 20 kernels of popcorn, right? We're going to put these in our little container, and we're going to pop them. Now we're done. Take it, dump it out, and here's what we get. If you count, we have 16 popped kernels and 4 duds. Our theoretical yield was 20, right? Our actual yield was 16. The percent yield is going to be 16 divided by 20 times 100. Our popcorn reaction went in 80%. That's all there is to percent yield. Any questions? Well, 80% is a pretty good yield for popcorn. Here we are doing a reaction with aluminum, sulfur, and we're making aluminum sulfide. We take 5 moles of sulfur, we do our calculation. We get a theoretical yield of 1.7 moles. We actually do the reaction. We get a little pile of powder, and we weigh it out and determine it's 1.5 moles. What's the percent yield? You simply identify the theoretical and the actual. You take the ratio, multiply by 100. Again, this all cancels. Multiply by 100, 88%. Now, just like we can do this stoichiometry exercise in terms of moles, we can also do it in terms of mass. Let's look at an example. Nitrogen monoxide reacting with oxygen gives nitrogen dioxide. Okay? We take 10 grams of NO, react it with excess oxygen, so that's in excess. We get 9.7 grams of NO2. What's the percent yield? Now, there are lots of ways you can do this problem. The simplest way, I think, is just to look at this and say, okay, 10 grams of NO are how many moles? Our ratio here is 1:1. If we know how many moles this is, we know our theoretical yield. Here's our molar masses. NO is 29.99, NO2 is 46. So 10 grams of NO are how many moles? 1 mole would be 30. We have 10. 10 mass divided by molar mass gives us moles, doesn't it? We've heard that before. 1/3 of a mole. Over here we get 9.7 grams of NO2. It's 46. Mass divided by molar mass is moles. What is that? 0.21. So we expected 0.33. we get 0.21. Quickly calculate the theoretical yield. Simply going to be 0.21 divided by 0.33 times 100. %. Any questions? Now, there are two tutorials on the website that did not make it onto Blackboard. The first one is called Limiting Reactants, and that's because I figured it was a real pain to do it twice, save that for general chemistry. The second one that didn't make it is this one. These seem like really simple problems, but the tutorial is not. For the reaction shown below, reaction of 15 grams of trifluoroethane, here's its mass, produces so many grams of CO. What's the percent yield? It's actually not that difficult, even though some of the problems really do get strange. But here's a mass, here's a molar mass. That gives us moles, right? Here's a mass, here's a molar mass. That's moles. All you have to do is adjust for the stoichiometry. So let's just do it quickly. 1 mole of trifluoroethane gives 2 moles of carbon monoxide. We'll do a mass ratio for the given in the denominator. Calculate the theoretical yield. Here's our mass ratio. 2 times 28, 1 times 84. 56 grams of CO for 84 grams of trifluoroethane. Okay. Here's our given. Here's our ratio. Do the simple calculation. 10 grams of CO. That's our theoretical yield. Now, the actual yield, 6.6 grams, right? So, here's our theoretical. Here's our actual. Percent yield is simply going to be the ratio times 100. And that's 63.8. Again, these are entirely possible problems to do, but they're annoying. So I didn't put them in the tutorials. Any questions? All right. Well, let me just repeat what I said at the start of class. Wednesday is lab makeup day. That means no class. Okay? We all got that. If you know somebody that isn't here, tell them no class Wednesday. On Wednesday, you can do the lab safety quiz if you like. Earn 6 points extra credit. Again, it's a really stupid, simple quiz. Everyone should get the full 6 points. You have 2 attempts at the quiz because it is so simple. Here's the tutorials we got for today. Chemical stoichiometry and mass ratios. We're up to 5. That's 25 points. 31 if you include the lab safety. All right, guys, I will see you back here, and we will do Chapter 7 next Monday. Remember the deal. 350 is your magic point to get an A and not have to take the final.
Cool.